Hello and welcome to the video lecture for Chapter 15. Here we're going to introduce temperature, heat, and expansion, and this is the first of a few chapters where we cover what is known as thermodynamics, which is essentially the physics of heat. Okay, so let's get talking about heat and temperature and those kind of related matters. Okay, so just a few topics to introduce here. What is temperature? What is heat? All right, how does that differ from something called the specific heat capacity, because they're really quite different quantities. And then we're going to quantify thermal expansion, so things heating up and getting bigger. Okay, so let's get temperature out of the way. All right, so temperature, something we take for granted, but how do we quantify it? It's a number that corresponds to the warmth or coldness of an object. It is measured with a thermometer. It is a per particle property, okay? So it is proportional to the average kinetic energy of the particles that make it up. So you can think of it as kinetic energy average, all right? It's not equal to the average kinetic energy of the particles that constitute the thing that you're measuring the temperature of, because particles are really small and their kinetic energy is tiny, because remember, it's 1/2 mv squared, but it's proportional to that, okay? At least to the average, and that's really what it represents, some proportionality, okay? But since it is this kind of unanchored proportionality, it needs its own units. So by introducing the temperature, we're going to introduce a new dimension, a new unit of physics, something we have not done up to this point, okay? By the way, there is no upper limit of temperature. My students love to ask me that. There are some theoretical ideas about the temperature of the Big Bang being an upper limit, but there's no real kind of agreed upon upper limit of temperature. There is definitely a lower limit. There is something called absolute zero. Okay, we'll talk about that. All right, so let's get into the unit of temperature. All right, so temperature is proportional to the average translational kinetic energy per particle in a substance. Yes, indeed. All right, that's just putting into a sentence what I jotted down in the previous slide. A gas, that means that's basically how fast the particles are bouncing to and fro. So that's really, kinetic energy in the sense of a little ball bouncing around. But it also applies to liquids. Those would be the particles sliding together, the sheets of loosely connected molecules. And for a solid, you can think of that lattice of molecules all interconnected through their molecular bonds jiggling around. Okay? So again, a thermometer, it measures temperature by expansion or contraction of a liquid. So it uses the last topic of this chapter, thermal expansion, in some quantifiable way. It's basically calibrated. Okay, so it's calibrated so that those changes mean something. If you think about a digital thermometer, it can use other mechanisms. It can use electromagnetic mechanisms, such as a change in resistivity of a wire, a temperature-dependent resistivity change. That's actually a very, very common way to measure temperature. That's also a good way to measure wind speed because of its association with wind chill. Furthermore, temperature can be measured through means of other circuitry elements, but resistivity is by far a really simple way of measuring temperature. Okay, but a more old-fashioned and kind of fundamental way would be this idea of thermal expansion. Okay. Reading occurs when the thermometer and the object reach thermal equilibrium. All right, that's when they're both the same temperature. That's not necessarily instantaneous. Okay, you think about a meat thermometer, it takes a minute for it to reach equilibrium. And infrared thermometers operate on another principle. They operate by sensing a particular radiation. How does that correspond to temperature? Well, we'll talk about that a bit when we talk about properties of light, but the key word here is something called Wien's law, which is something I always cover in my astronomy classes, but it's this really amazing law, and it only applies to solids. It doesn't work for gases, by the way, or liquids. But it tells you that color means temperature. There's a direct relationship. There's a functional relationship between the two, which is remarkable. It's not perfect, but it is pretty good relationship between the two. Okay? All right, so let's get into those temperature scales, right? That new unit I mentioned. Okay, so first of all, let's start with the oldest temperature scale first, which is the second one down, the Fahrenheit temperature scale. Okay, so this was developed by a man here that lived between 1686 and 1736. And this temperature scale has 32 degrees as freezing and 212 degrees for boiling water, which seem like really weird choices, but that was not the purpose of the Fahrenheit scale. The Fahrenheit scale was meant to be a anthropocentric type of temperature scale, and anthropocentric just means that it's human focused. So essentially a change in Fahrenheit is really easy to recognize. The temperatures that we tend to experience as, Earth weather are going to fall in numbers that make intuitive sense to us. I mean, just think, for example, that a 1 degree change in Fahrenheit is a smaller scale than a 1 degree change in Celsius, the next temperature scale we're just about to talk about. That means it's more granular, and that's better for actually describing the human experience. If I say the difference between 30 degrees Celsius and 31 degrees Celsius, well, that's a pretty big jump, right? So am I going to use a decimal? No, not in everyday language, but you can then describe those integer changes in the Fahrenheit scale. So definitely it actually has its advantages as an everyday temperature scale, but it really is not well suited to chemistry or science, okay? Now Celsius, we could say, is very well suited to chemistry, all right? Because it's got 0 degrees Celsius for freezing and 100 degrees Celsius for boiling, all right? And why do I say chemistry and not physics? Well, because it is pretty much focused on taking experiments in a laboratory at sea level, because water only boils at 100 degrees Celsius at sea level, right? And it's very much, that's not true in space. That's not a general statement, so it is this, it's focused on the properties of water, which are very important, for certain types of laboratory experiments, and it has advantages for that. And it is widely used as the everyday temperature in most countries other than the United States, so it has been kind of adopted as a non-scientific type of temperature scale, but it still is a useful one, right? But it's very much focused on water, right? Water is incredibly important, but let's take that in consideration. Now, the best temperature scale by far, and one that is used by most chemists, really, but certainly used by all physicists, is the Kelvin scale. All right, the Kelvin scale is really the scale we're going to talk about. It's the one we care about. All right, it came last. All right, Lord Kelvin, who lived from 1824 to 1907. And what sets the Kelvin scale apart from the others right away is that 0 degrees Kelvin is absolute zero. It is a theoretical value that can never be reached as far as we know, but represents the point at which all molecular motion ceases. Okay? The change is the same as Celsius, so it adopted something that was already used by the scientific community, the Celsius scale. So if you go up 1 Kelvin, that's the same as going up 1 degree Celsius. All right, and kelvins rather than degrees are used. Okay, all right, okay. And what I mean by that is that when we talk about changes in Kelvin, we don't say degrees Kelvin, we just say Kelvin. Okay, all right. So by the way, boiling water is at 373, which means that freezing 0 degrees Celsius corresponds to 273 Kelvin, right? And that's a good kind of conversion factor there. Okay, so there's twice as much molecular kinetic energy in 2 liters of boiling water as in 1 liter of boiling water, which will be the same for both. Okay, think about how the definition of temperature, it's proportional to the average kinetic energy. So is it going to go up when there's more of a substance? What does your everyday experience tell you? Definitely not. Okay? Temperature is independent of the amount of substance. Okay? It is proportional to a per particle quantity, right? So that's what we see. It doesn't matter how much you have of something. It just depends what the average part of that something is doing, whether it's that jiggling solid or that bouncing around gas molecule. Okay? So to say that body A has a higher temperature than body B is to say that body A has what? Right? Well, I think you know it, right? If you don't, then you're not paying attention. It's kinetic energy per particle, okay? That's a key idea, all right? And maybe you haven't thought about that being really the definition of temperature, but it is. It's definitely one you want to take note of, okay? So that's temperature, but let's talk about a different idea altogether, and that's heat. And heat is something we've already seen before, because heat, it turns out, is going to be measured in joules. So heat is an energy, all right? Temperature definitely is not. The Kelvin is a new unit. At this point, because if you think about the fact that the joule is just composed of units we've seen before, right? So that means we're going back to mass, distance, and time. But that joule, or rather that Kelvin, the Kelvin, is a new unit altogether. So if you're keeping count, that means at this point we have 4 units. Okay? We'll get one more before we really wrap up the semester, okay? But that's because physics is all about breaking things down into the simplest ideas possible and saying that all the universe is described by basically 5 fundamental units is a pretty simple way of talking about things, right? It's a fundamental way. Physics is a fundamental science. Okay? All right. But anyway, heat is something we've talked about before. It's energy. And it's energy that has to do with temperature changes. Okay? Because energy is just an accounting method. It's just a convenience. It's just a way for us, to think about the world and make sense of it. It's not new physics in the way that Newton's laws are new physics. It's not new physics in the way that universal gravitation is new physics. It's just convenient, okay? And that's all energy is. And so then if energy is going to be convenient, we should find a way to apply it to temperature as well. Okay, so hopefully you kind of see the motivation behind heat. Nothing new, just a convenience. Okay, so what is it? It's internal energy transferred from one thing to another due to a temperature difference. Okay, so energy, internal energy, so there's energy possessed by an object, okay, or a substance or a system, whatever you may be looking at. All right, and it's internal energy in transit. Okay, so it has to do with the flow. See, transit, flow. It's all about change. So from a high temperature substance to a low temperature substance, heat will flow, okay, until equilibrium is reached. So heat will flow from object A to object B. We'll have a flow of heat. All right? Internal energy never flows unassisted from a low temperature to a high temperature substance. Okay? So there's always a directionality. We'll learn that that's actually part and parcel of the second law of thermodynamics. But for now, we'll just kind of, take that as gospel. Heat only flows in one direction. It flows in the downhill temperature direction. Okay? So internal energy would be possessed by object A, possessed by object B, and heat flows between them. There's an analogy here. And the analogy is potential energy and work. Okay? So a force does work on an object, but an object never possesses work. An object possesses kinetic energy or potential energy. Right? Potential energy being the best analogy to an internal energy because it has the potential to do something. Internal energy has potential to allow heat flow. So heat is like work. Internal energy is like potential energy. Okay? Make sense? Okay. So in a red hot thumbtack, or if a red hot thumbtack is immersed in warm water, the direction of heat flow will be from, okay, think about the way it has to go. It's going to be from the hot thing to the cooler thing, from the red hot thumbtack to the warm water. All right? So let's quantify it some more. How do we talk about heat? Well, we can certainly measure it in joules, right? We can fall back on that as the sort of the basic derived unit because again, it is a kilogram meter squared per second squared, but that is still, very much a basic unit. A calorie is another unit of temperature, but it just has some conversion factor to a joule. All right, so this would not be composed of SI units. Okay, think about the calorie gets used quite a bit, and you're going to be accountable for converting back and forth. But hey, as far as problems go, conversion problems aren't that bad, right? So 4.18 joules of heat are required to change the temperature of 1 gram of water by 1 Celsius degree. That's how the calorie is defined. So that 4.18 joule is defined as the calorie. All right. Likewise, 4,186 joules is defined as the kilocalorie. All right. And that, by the way, is equal to the calorie with a capital C, and that's what you see on food packaging. So if you're eating a snack that has 100 calories, that would be calorie with a capital C, which the rest of the world calls kilocalories, by the way. If you look at food packaging, basically anywhere else in the world, they don't call it calories, they call it kcal. And that then would be equal to 100 times 4,186 joules, or 400,000, approximately, joules. That's too big, right? Well, no, that's actually how much energy is in that food. It just goes to show that metabolic energy is huge. Because 400,000 joules, I mean, that'd be like dropping a 4,000 kilogram car, times 100 meters, right? That's dropping a you have to multiply by 10, so 10 meters. So you take a 4,000 kilogram car, its weight would be 40,000 newtons, because approximately 4,000 times 10. Okay, so again, 4,000 kilograms becomes 40,000 newtons on the surface of Earth. And then work is weight times time, in this case, weight times distance, in this instance. So then multiply by 10 again, and you got 400,000, okay? So again, 100, too many numbers to keep track of without me writing it down, at least for you, right? So 100 calories is equal to approximately 400,000 joules, okay? Well, then that would be equal to a 4,000 kilogram car or large object. That's a huge object, 4,000 kilograms, right? That's like a big truck, times gravitational acceleration, which we can approximate as 10 meters per second squared, and then times 10 meters, right? Because 4,000 times 10 times 10 is 400,000, okay? Because it's just 4,000 times 100, all right? And so that would give you the correct units of dropping this big giant truck 10 meters, and 10 meters is like 30 feet. I mean, you think about that. You drop a big giant truck from 30 feet. When it hits the ground, I mean, that's going to make a huge giant dent. I mean, there's going to be a huge release of energy. You're going to hear a giant smashing sound. I mean, think about how much energy that is. That's how much energy there is in a 100-calorie snack. That's amazing. That is mind-boggling. Just what's happening at the chemical level in a metabolic machine like a mammal. It's so much energy. Okay? All right. I mean, biology is amazing like that. Okay, so anyway, quantity of heat continued. Energy ratings of food and fuels are determined from the energy released when they are burned. Okay, that's what I'm getting at about eating a food, right? So the unit of energy, the calorie, there it is with capital C, is common for foods. So the heat unit for labeling foods, the kilocalorie, or 1,000 calories is called a calorie, right? That's exactly what I was talking about. Heat needed to change the temperature of 1 kilogram of water 1 degree Celsius, okay? So instead of 1 gram, because it's 1,000 times as much, okay? So the same quantity of heat is added to different amounts of water in 2 equal sized containers. The temperature of the smaller amount of water, all right? Well, what happens? Does it decrease more, increase more, does not change, not enough information? What do you think? Okay? It increases more, all right? Because having less mass means less heat is needed, okay? We saw that it was dependent on the amount of mass, right? And that makes intuitive sense, okay? So you heat a half cup of tea and its temperature rises by 4 degrees Celsius. How much will the temperature rise if you add the same amount of heat to a full cup of tea? All right? Bet you have a guess. Absolutely. It's proportional, right? Double the mass, you would have to double the energy if you want the same temperature change, okay? So you see, and this is just based on that definition, the fact that the calorie is defined as, how much heat it takes. So that's why I'm saying there's a direct proportionality, okay? All right, well, we can actually quantify that direct proportionality, and we can do it with the definition of specific heat capacity. This is just going to be a way to talk about how much energy it takes per degree per gram to heat something up, or per Kelvin per kilogram to heat something up, okay? So, specific heat capacity, what is it? Well, it is defined as the quantity of heat required to change the temperature of a unit mass of substance by 1 degree Celsius. And by the way, a delta degree Celsius is equal to a delta Kelvin, okay? And that's a great thing about changes. Because, sure, we have to remember that, 0 degrees Celsius is 273 degrees Kelvin. You got to make sure you get that right in certain cases. But in many cases, if you're only interested in a change of temperature, you don't even have to worry about converting from Celsius to Kelvin or from Kelvin to Celsius, because you're good to go, because the changes are equal. All right? Okay? Like thermal inertia, resistance of a substance to change in temperature. Okay? So that's a great way to think about it. Let's unpack that a little bit. Thermal inertia. Remember, inertia was the sluggishness of matter. The more massive something is, the harder it is to accelerate it. Same idea here. The more heat capacity a substance has, the harder it is to heat it up. The more energy it takes to heat it up 1 degree or 1 Kelvin. So that means that as we look at different substances, we should expect some substances to have higher heat capacities than others. All right? So think about something that's really easy to heat up. You thinking of something? Something that gets hot really easily. Okay? Metal, right? Certain metals, you leave them out in the sun, they're hot to the touch really easily, right? So that means that a metal must have a low specific heat capacity. It must not have very much thermal inertia, okay? When it's not literally its mass, it's just the quantity of that particular substance, okay? Now, what about something that has really high thermal inertia, that has a high specific heat capacity, something that doesn't heat up very easily in the sun? Well, water, right? Water's still cool to the touch, even when it's been out in the sun, right? Okay, all right. So different substances have different thermal capacities for storing energy. Example, it takes about 2 minutes to raise the temperature of an iron pot of water to boiling temperature. And the minutes here, don't think here that we're saying that heat capacity is fundamentally a time-dependent phenomenon. We're just assuming that this is 2 minutes of adding heat at a fixed rate. All right, so the time here is just kind of a convenience, a way to visualize something, to actually think about it in real terms, but there's not an actual, because it depends on the rate. So we need to assume that we're adding heat at a steady rate. Okay? And we'd then add heat at that same steady rate to water in order to make this comparison. Right? So it takes less than a minute to raise the temperature of the same quantity of water in a silver pot to boiling temperature. Okay? So, continuing of heat capacity, right? Getting to the actual quantified, the equation, the way we're going to actually solve problems. Equal masses of different materials require different quantities of heat to change their temperatures by a specific number of degrees. Okay? I basically said this, but it's good to have it in a confined sentence like this. Okay? A defined and confined sentence. 1 gram of water requires 1 calorie of energy to raise the temperature 1 degree Celsius. Okay? We've established that, right? And that is 4.186 joules. All right? So 1 calorie is 4.186 joules. All right. 1 gram of iron, on the other hand, requires 1/8 as much. There we have a direct quantified comparison between the two. As much energy for the same temperature increase. Therefore, water absorbs more heat than iron for the same change in temperature. Water has a higher specific heat. Okay. So how much, it would take 1/8 as much energy. Okay. So the high specific heat capacity of water. It has a higher capacity for storing energy than almost any other substance. Really, it's remarkable, all right? And the only other really even remotely common substance that has a higher heat capacity, and really, you can look at all kinds of different chemical combinations, but the one out there is liquid ammonia, all right? Liquid ammonia, like you would find on Titan, the moon, one of the moons of Saturn, the only moon in our solar system that has an atmosphere, interestingly. But that moon that has lakes of liquid ammonia, and those lakes have a higher heat capacity than water. All right, that's about it. Truly and honestly, there's no metals that have higher heat capacity. There's no rocks that have higher heat capacity than water. None, not even close. Okay, so it involves various ways that energy can be absorbed. So essentially, the molecules have lots of ways they can absorb the energy. They can increase their jiggling motion. They can increase the amount of inertial vibration. Water molecules can absorb energy without increasing translational kinetic energy. So because of that complicated way that all the molecules can interact and absorb that energy, that means that they're not translating and bouncing around much. They're doing other things. That energy is going to other places. So at the molecular level, at the level of treating molecules like little combinations of masses and springs, okay, that's the explanation of why water has such a high heat capacity, which is a neat way of thinking about it. Okay, it's not the primary way we're going to think about heat capacity. We're mostly just going to worry about the macroscopic consequence of it. But if you're curious about why water has such a heat capacity, this is the kind of quick summary. Okay, so specific heat capacities affect climate. All right, so this is the idea that the oceans being such a sink for heat capacity, being able to absorb so much energy, they can drive big climate effects. That's where you get things like the jet stream. All right, I'm just going to let you read over this example. It's fascinating, but I'm going to focus on the main topics here. Okay, but here's a good example that I do want to make sure we can cover. So, which has the higher specific heat capacity, water or land? Okay, but you know the answer, water, of course. Okay, absolutely, right? So, between a lake and the shore, the water has a much higher heat capacity. It's going to be able to absorb much more energy for a temperature change. Okay, all right. So, on to thermal expansion. So, due to the rise in temperature of a substance, molecules jiggle faster and move further apart. All right. So, even solids, where they're all kind of fixed in place, they're not entirely. Okay, the distance between them will start to increase effectively as they move about. Okay, so most substances expand when heated and contract when cooled. Okay, there are some exceptions, but absolutely. So railroad tracks, for example, laid on winter days expand and can buckle in the hot summer. That's why they're laid with gaps between them. If you look at railroad tracks, okay. Warming metal lids on glass jars under hot water loosens the lid by more expansion of the lid than the jar. All right. That's a good way to get the lid loose. All right. So, all right, here's an example of a railroad track that was not enough gaps were created. All right, and it absolutely buckled underneath the on a very hot day. Okay. So thermal expansion can cause bending and can be a mechanism of a very basic type of thermometer. And so this is the idea of a bimetallic strip, okay? So different substances expand at different rates, just like different substances have different specific heat capacities. There's something called the coefficient of thermal expansion, which is material specific. So when the temperature of a bimetallic strip of brass and iron is increased, the greater expansion occurs for the brass. So the brass has a ability to expand more for the same temperature change, because there's going to be thermal equilibrium between the brass and the iron, but the brass stretches out more for that same temperature than the iron. All right, so that bends to turn a pointer, to regulate a valve, or to close a switch. All right, so it is a very effective temperature-driven switch mechanism. All right, so here, for example, if we cool the whole bimetallic strip, then it's going to bend towards the ice. All right, because what's happening is the brass is going to shrink more than the iron. That means that the curvature is going to be on the part that shrunk more. That's why it's curved this way. On the other hand, if you heat something up, and it doesn't matter which side you heat it up on, if you heat something up, then the brass is going to expand more, so then the brass is on the outside of the curvature. So cooling, brass is on the inside of the curvature. Heating, brass is on the outside of the curvature. Both explained by the fact that brass changes in length more for any temperature change, whether it's a decrease or an increase. Okay? All right? So when a stringing telephone line between poles or when stringing telephone lines between poles in the summer, it is advisable to allow the lines to do what? Okay? So what's going to happen? Think about the summer. What's going to be the state of the telephone lines compared to in the winter? Okay? Sag, right? Because they're expanded. They're longer than they will be. What's going to happen in the winter? They're going to contract to a length that's shorter. If you attach them taut in the summer, they're going to snap in the winter. Okay? So thermal expansion is increases in expansion are greater in liquids than solids. All right? Significantly so. All right? Solids, we're talking less than 1% in terms of the actual change in length, for example. But liquids, it can be much more dramatic. Gases, even more so. So overflow of gasoline from a car's tank on a hot day. Okay, if the liquid gas gets very hot, right? Of course, gasoline, but of course it's a liquid. All right. Gasoline underground is cool, but when placed in the car's tank, it warms and expands. All right. Here's an example of expansion of water. Right. So water is an interesting case. So when water becomes ice, it expands. Ice has an open structured crystal, which results from strong bonds at certain angles that increase its volume. This makes ice less dense than water. That's unusual for solids. Solids are almost always denser than their liquid state. Water is the exception. All right. Furthermore, thermal expansion of water has another oddity besides ice being less dense than the liquid. As temperature of water at 0 degrees, so this would be water that's just melted. Okay, but so at 0 degrees you can have, and we talk about phase changes a bit more later. But at 0 degrees, you can have both a solid state and a liquid state for water, right? Again, at atmospheric pressure, because, of course, freezing is dependent on the pressure. But let's assume that we have, liquid at 0 degrees. So more of the remaining ice crystals collapse, okay? The melting of these ice crystals further decreases the volume of the water. Two opposite processes occur at the same time, the contraction and expansion. All right, so volume decreases as the ice crystals collapse, while volume increases due to the greater molecular motion. The collapsing effect dominates until the temperature reaches 4 degrees Celsius. After that, the expansion overrides the contraction because most of the ice crystals have melted. What this looks like on a temperature scale then is we can look, and if we zoom in at the temperature difference between 0 and 18 degrees Celsius, all right, 18 is still pretty cool, all right, it's getting on the warm side. We can see that there is a dip in the density that occurs between 0 and 4. So 0.2 is the least dense that water can be. All right, so 4 degree Celsius water is the least dense, all right, as far as the liquid state. After that, it's then going to start, excuse me, I kept saying least dense. Let me correct myself there. It is the most dense, because after that, the density is then going to decrease because the volume will increase. And then the density will continue to decrease as the water becomes warmer and warmer. Now, is it a big density change? Well, look at the volume. Absolutely not, right? So if we go from 0 degrees up to right to the point where it starts to boil, we can see that there is a density change of only about 6%, okay? So because a volume that did take up a space of 1 liter now takes up a space of 1.06 liters, but the mass hasn't changed, all right? So the volume has increased by 6%, the mass has not changed, therefore the density change has been the reciprocal of 1.06, all right? So not quite a 6% reduction, but a definitely less than 10% reduction in the density of the water, okay? So not a big difference, and that's between water that went from 0 degrees all up to being about ready to boil. So water that's about ready to boil is measurably less dense, okay? Because it's taking up more space. Not a lot, but something in the low percentages, less than 10%. And so that means that this difference between 0 and 4 is smaller still. You can see it's 0.002, right? So it's actually a very subtle effect, and it would only matter for certain cases. It's something we consider in the oceans, and it's something you consider in certain experiments, that you can get the most dense water at 4 degrees Celsius, okay? But of course, if you freeze water, then the density decreases quite a bit, right? It decreases up to almost 10%, because we have that ice is about only 90% as dense as water. And then if you go on the other end, if you boil something, well then look, the density, it becomes incredibly less, because of course gases aren't very dense. It actually just depends on how you confine them. And so then of course that's why we see there's a huge jump in water vapor, shown by this symbol here, that is no longer on the same scale. And then water vapor is very, very low density as it continues to just expand out to fill its space. Okay? All right, so thermal expansion of water. When ice freezes to become a solid ice, its volume increases tremendously. As solid ice cools further, it contracts. Density of ice at any temperature is much lower. Excuse me. Which is why ice floats. Okay? So when a sample of 0 degree water is heated, it first, we talked about this, the density is going to go up, which means it contracts, okay, until it reaches 4 degrees, and that's the densest water can be, all right, liquid water. When a sample of 4 degree water is cooled, it expands, okay? It's actually going to become slightly less dense. All right, so that's it. There's a brief introduction to a couple ideas. I had 3 ideas. What is temperature? How do we define it? What is specific heat capacity, and how it's really specific, right? Different materials have different amounts of energy it takes to heat them up. And then last of all, what's the idea behind thermal expansion? How does it apply to water as an important example of liquid, and how does it apply to metals and its application for bimetallic strips? Okay, so that's it. That's what you need to remember from this chapter. Okay, we'll be talking more about temperature and heat in future chapters. Thank you so much for watching this video.